All right, everybody. What we're going to do today is talk about something new. So we're going to leave this world of regular languages behind. Regular languages are anything described by a regular expression, a DFA or an NFA. They use machines that can only describe kind of their memory using states, which makes that memory very modular. It doesn't actually have memory. It's a state-based machine. This place that we're moving to are called context-free languages, and in specific, our first step into context-free languages are context-free grammars. So a context-free grammar looks a lot like this, okay? This is what we're looking at here. This is a context-free grammar. And what it is a list of variables on the left-hand side and a bunch of replacement rules or productions on the right-hand side. So this says the variable s can be replaced by ASB or T. Normally, uppercase characters are variables, and then lowercase characters or whatever your alphabet is. That's not a very good sigma. Here we go. Whatever your alphabet is are the terminals. And so in this case, you have a starting symbol. It's usually the first rule on the top left of your list of rules. And you generate strings in the language by continually replacing the variables in your language until you end up with only a string of terminals. And then that string is a string accepted by your grammar. So that was a lot of stuff really fast. So I will scroll up to some text. You can pause and kind of read that. I will scroll past some more text here. As an example of a way to derive a string in this language, you take your starting symbol, you replace it with something. So in this case, S is replaced by ASB. And then you pick a variable in this expression. There's only one, so we have to pick that one. And you replace that with something. In this case, I'm replacing it with T. And then you take that next variable, you replace it with something. In this case, I'm replacing it with CTD. That's one of the options for T. And then lastly, I'm replacing T by CD. So I would say this string can be derived in this way. And so we see that A, C, C, D, D, B is a string in our language. One thing that you should notice as you're looking at these rules is that you can never generate an A without generating a B. And so there's some sort of matching going on here. And you can never generate a C without seeing a D. So that matching is super interesting. Let's start with some things simpler and have you derive some strings in a simpler grammar. So here is a simple grammar that I want to see you generate a few strings for. So go ahead and pause, generate a few strings for this. Show me what you get. Okay, hopefully you're back. And the question is, what language is this? After you see the strings that are generated by this, you tell me what language this is. So here are some strings generated by this grammar. Right? What language does that start to look like? Hopefully you get something like A star out of that. This is a language that recognizes, this is a grammar that recognizes a regular language. That's okay. Grammars can do that. Let's try another one that has some matching in it. And the reason I say matching is because in this one, you can't generate a 0 without a 1. Go ahead and pause the video and write a few strings related to this. I'll wait till you're back. Okay, hopefully you're back. So my first question is, can this grammar generate the epsilon? Can it generate the empty string? And the answer is yes. I can just take my starting symbol and replace it with epsilon directly. And what language does this describe? And this is a little harder, but if you write down some of the strings that this thing generated, hopefully you start to see a pattern. And this is usually the first language that you prove is not regular, right? 0 to the n, 1 to the n. So this grammar definitely can do some things that our regular languages could not. It can do some matching that our regular languages couldn't, which is great. Let's try a grammar with some multiple variables, and we'll have some questions here. So go ahead and generate some strings from this particular language and tell me what you get. Maybe answer some of these questions while you're along with it. I'll pause, come back. Can this generate only A's? Your answer should have been yes, and part of the reason for that is I can generate a bunch of A's using this, and then I can terminate the S with an epsilon, which ends my production. Can I generate only B's? The answer is yes. I can start off by replacing my S with T, and then generate B's until I'm done, and I get an epsilon to end my production. And what language does it generate? And so this is something like A star, B star, looks like. And I'll let your generated strings verify that or not. Hopefully I have that right. We're pushing on 5 minutes. So I think I will save the next parts of this for next time as a brief preview. Often I'll say that we show our derivations of a particular string with a tree. And so this is an example of that, and this is called a parse tree. We'll push on that a little bit more next time because parse trees start to become important to talk about other properties of context-free languages. But we'll leave this one here. So this is a brief introduction into context-free grammars. Hope you enjoyed it. As always, be kind to each other, and in order to do that, you need to be kind to yourself. See you all next time. Bye.